Hello, everyone. Thank you for coming to one of the last few events of this term and that year. Today, we have our guest speaker from London, Pandu Raharja-Liu. He is the co-founder and CTO of Panakeia Technologies. With a background in maths and engineering, he has well over a decade of experience in applying machine learning research to cancer research, drug discovery, as well as working on scalability and reliability. So without further ado, I'll pass it on to Pandu. And yeah, welcome, David.
Cool. Thanks, everyone. I'll share screen. Good. David, do I need to share screen for recording or not? I think
Yes, please.
Yeah. So yeah, thanks everyone. Good evening. So yeah, my name is Pandu, the co-founder and CTO of Panakeia. I guess before we start to the contents, trying to sort of walk everyone with who we are as a company. We are a remote AI company, so everyone in our company works remotely. We sort of come together once in a while, discussing ideas, having town hall, etc. But pretty much a lot of our work are done remotely. We are based in London, as you can imagine. Most of the employees are, sort of living around London area. We have some people who live in Cambridge area, and recently and increasingly we also have sort of growing presence in Munich, Germany, where I came from. And yeah, we are as a team, we are a very multidisciplinary sort of companies. We have a good balanced combination of ML scientists, engineers, clinicians, biologists, biochemists. We have, of course, we're an AI company, so we have a strong team of ML research, platform engineering team, and sort of biological clinical team who are, of course, dealing with the clinical elements of the work, biological elements, as well as business development, etc. So yeah, as a company, our mission is to sort of understand cancer better using AI, how cancer evolved, how it came into being, sort of like how actually can we characterize it better, can we treat it better, sort of stopping it as a deadly disease as we know today. Yeah, and one of the strong sort of vision that we have as a company is, to sort of help democratizing cancer diagnosis worldwide. I don't know if, some of you may be studying medicine, cancer as a disease. Of course, it is an aging-related disease, right? The older you are, the more likelihood you would get cancer. It is also diseases that, unfortunately, very sort of unequal or not as equitable as other disease, because it is a expensive sort of disease to treat, to diagnose, etc. So you might imagine that in countries in Africa, for example, or in South Asia or in Southeast Asia, cancer as a disease is actually, it's still very deadly, non-treatable in some circumstances, and extremely expensive, right? Even the method and the means to diagnose cancer are not necessarily there in a lot of countries. UK, for example, as a country, it has run about, I think it's like 1,500 to 2,000 pathologists, for 65 million population. In India, for example, a country that is 20 times the size of UK, it only has the same amount of pathologists. So you can actually imagine that there is actually a lot of inequity when it comes to cancer diagnosis. And I guess, our company mission is, aside from understanding cancer better, we would like to provide, sort of state-of-the-art cancer diagnosis and treatment recommendation to pretty much everyone around the world. Yeah, and so what we're doing at the moment, how we are specifically achieving this vision is we're developing what we call the next generation of molecular tests. I don't know, does anyone know or can give example what kind of molecular tests are out there? Has anyone done lateral flow for COVID, PCR? So those are actually examples of molecular tests. The idea is to diagnose disease, to characterize disease, you need to do all this molecular tests, right? To better, well, first, to detect if there is a presence of certain diseases, right? Virus or bacteria in your body. Another way of diagnosing that or characterizing diseases to see, what kind of type of disease do you have, right? There are actually certain tests that subtype certain diseases, for example, right? So all these sort of things are done, of course, in a wet lab. It is highly specialized. A lot of people literally spend 5 years doing PhD to be able to practice this sort of test, right? So it's not necessarily something that is easy or cost effective to do. So our mission is to develop the next generation of molecular tests that is computational, i.e., we hope that in the tasks that we are working on, that we can actually replace those using our computational method. So that is something that is exciting because, of course, it is computational, i.e., we just run the analysis, right? You get the results out without doing all this staining, molecular tests, right? The sequencing, which is expensive and time consuming. Just like giving a context in terms of how cancer used to be diagnosed, long time ago. So the idea is, most of the time, of course, someone would sort of felt this lump in their body, or there's a bleeding in parts of your body, right? One of the most common symptom of cancer is actually bleeding in, let's say, in your feces or in your skin or any parts of the body. And, you go to see a doctor, and doctor would sort of like look into your body, maybe sort of trying to see if there's a lump. If there's a lump, they would recommend you to go to hospital, of course. And first thing they would do is to do this radiography screening, right? MRI, CT scan, mammography, all this black and white imaging, trying to see if there's actually sort of early sign of cancer, that sort of white spot over there, there's a calcification, usually means that there's actually a potential cancer on the patient. And upon that, the tissue is taken from the body because they need to see, right, is it actually really cancer they're looking for? Or is it some sort of like other sort of anomalies that aren't necessarily dangerous? Because, some cancer or some anomalies are deadly, right? Some cancer is extremely aggressive. Other cancers barely sort of grow, just stay there. Actually you die first without the cancer ever doing harm to your body, or it's just like some random, anomaly that are not necessarily dangerous. And then after that, pathologists, which is actually highly subspecialized clinicians, they would look into the tissue, they would analyze that, they would sort of make a diagnosis, right? The person has a, malignant breast cancer. And based on that analysis and diagnosis, the patient will then undergo what I call surgery or chemotherapy. So, chemotherapy is, of course, applying certain chemicals in your body, right? The good old chemotherapies are usually non-specific, i.e., let's say if you get breast cancer, they would just apply certain chemicals, which may actually be deadly, dangerous, toxic, etc., to your body. So as you can see, this is a bit like, how we as a normal people sort of treating coldness or flu, right? You're having headache, just apply tamoxifen, ibuprofen or aspirin, and then hopefully the symptom gets better. So it's not necessarily precise, specific, targeted, but that's how it was done. Still very deadly at the time because there was no much understanding on how cancer works, et cetera, et cetera, et cetera. And I think things start changing around the middle of last century. We sort of grew the understanding on how cancer came into being, right? How the body actually developed cancer. What is cancer as a cell or as a family of cells? One of the things that is very interesting is the discovery of what's called estrogen receptor. So this is like a protein that are on the cell surface. If you look biology in high school, right? The cell surface, the cell membrane, a lot of cell signaling, how cell divides, died, etc., were controlled by or were induced by this cell surface protein. And one of the earliest that was discovered is actually this called ER, the estrogen receptor, discovered in 1957, found on the cell membrane. And it turns out actually that is actually quite important for cancer dynamics. And certain smart people around 60s, or they were actually trying to target these molecules or proteins on the cell or cancer cells with the hope that they can perhaps stop the growth of cancer. And in 1962, tamoxifen was synthesized for the first time. What it does is actually it targets ER and it prevents cell growth. So the idea is if we can stop cancer cells from growing, we can treat them. And this is pretty much one of the very first sort of way that people treat cancer or target cancer, specifically, using certain understanding of, biology and biochemistry. So tamoxifen nowadays is, of course, one of the most important and effective breast cancer treatment. It is actually part of what's so-called WHO essential medicine, alongside aspirin, ibuprofen, extremely important, extremely available worldwide. One of the first example of how understanding cancer actually helps improve treatment, survival, et cetera, et cetera, et cetera. As a society, I think we sort of learn a lot more when it comes to cancer. It is one of the most studied research or medical area in the world for the last decades, and a lot of Nobel Prizes actually sort of happen, or discoveries happen while researching cancer. So what happened is, in the last 50, 60 years, the sort of targets that the clinicians, sort of were trying to intervene when it comes to cancer has grown dramatically. Today, I just took a look at this list of tests that was provided by Leica, one of the largest provider of the tests. And as you can see, there's so many tests that are actually specifically deployed to understand the biomarker of the tissue. And most of them are for cancer because, of course, it is the most targeted disease in the world. On top of that, there are actually hundreds of other tests, including DNA sequencing, which is, pretty much parts of our daily life nowadays. Whenever we want to go to the airport, right, we have to do PCR testing, and that is actually one example of the DNA sequencing. So, 5 decades in, the modern diagnosis is actually becoming extremely time-consuming, expensive. Still same, we still sort of analyze the tissue from the patient. Pathologist still looks into the tissue. It becomes more complicated because now we understand a lot more in terms of disease. However, on top of that, we have this plethora of tests that are being done once diagnosis is made by pathologists. We have the PCR, right, in a similar fashion to the COVID PCR test. We have genomic tests, whole genome sequencing. We have, immunohistochemistry. We have in situ hybridization and transcriptomics, a lot of tests. A lot of them are extremely expensive, extremely specialized. Even in UK, only a very few hospitals actually can do some of these tests. And this is something that, extremely, I would say, non-accessible to a lot of people. So as a company, we decided let's tackle this problem because, computational power is available anywhere. Each of you, I'm sure, has at least one smartphone, one laptop. Each of them can easily sort of do complex computational methods that actually we can sort of leverage to diagnose or understand cancer better. Yeah, and beyond that, after the tests, right, the targeted treatment is being done, and you can imagine that this additional test takes weeks, right? I don't know if some of you are trying to go to, other countries. They usually have this turnaround time of at least 24 hours when it comes to PCR. It is actually highly accelerated. In cancer diagnosis, a lot of tests actually takes days, if not weeks, if not months. Some of the tests actually need to be sent over to the States because that's like the only lab in the world who can do that. And it is expensive. Our simple PCR costs like what, 50, 150 quid. Some of the tests can take easily 5,000, 10,000 just to run one test. And that's like, I guess, the requirement for us to be able to understand the cancer better and hopefully treat the patient better, right? Because better understanding of cancer means pretty much either the patient would die because they couldn't survive, or the treatment wouldn't sort of work on the patient, or the patient would survive. So people actually go a long way in terms of the tests, the understanding of cancer. Yeah, and all these things actually happen before treatment, right? After the sample is taken, the analysis is being done, the test takes a lot of time. So one can imagine actually in a modern cancer diagnosis, a lot of time are actually spent waiting, because once it's determined, treatment can be scheduled. Some treatment are quite instantaneous in terms of surgery. some treatment take months, but even waiting for that, I don't know, some of you have family who experienced cancer before, that could be actually very excruciating in terms of sort of psychological challenge regarding cancer. And going to the AI, we're all here in a, I guess, interested or practicing AI on our daily basis. Our platform solved this by actually introducing a computational method of doing molecular tests. I guess at this point, it is quite obvious that computational or molecular tests are extremely expensive, time-consuming, specialized, non-accessible, whatever you can imagine, right? From something that is coming fresh from the research in the last couple of decades. And what we're trying to do is, we still take, or in our scenario, the way we see it, the tissue is still taken from the patient, and the pathologist still needs to do diagnosis on that. However, as soon as this tissue becomes available, our platform kicks in. It sort of analyzes the biopsy tissue, the tissue imaging coming from the patient, and pretty much provide this inferred molecular profiles. Based on this, then the treatment can be done. As you can imagine, it is much more time efficient, right? Computational, even heavy duty machine learning computations usually take what, minutes, seconds, right? So instead of waiting all these tests to come to the pathologist, you can provide pretty much a lot of things instantaneously. And of course, it is computational. It technically doesn't cost a lot of money. It barely costs money. But as a business, of course, we have to capture some value. And even after incorporating those things, we still can realistically provide the whole diagnostic information, within, let's say, 10% or within 10% of what it would cost if it's done in a wet lab. Of course, we don't need to sort of send the sample abroad or send a sample to hospital like Edinburgh and in London. We don't have to employ specialized biomedical scientists to do the test. We don't have to buy these extremely expensive reagents that cost easily 10,000 per vat, et cetera, et cetera, et cetera. Everything's computational. The only thing you need to have is a GPU, right? So that's like what we're doing as a company. And yeah, how are we pretty much doing that? I guess on a very high level, you're looking at biopsy tissue. So there are actually some patterns that have been understood by pathologists to be related to something, belonging to certain categories, molecular wise. So going back to the ER, right, one of the most understood molecule within our body, there are actually certain differentiation. If you look at this 4 examples from 4 patients, the ER negative patient, the patient which actually doesn't have ER expression, you can actually see the cells, it looks more structured, right? A lot of architecture are maintained. The one which express ER, for example, you sort of see that the cells are sort of growing, right? It sort of lacks a structure. The whole tissue is sort of, so it's sort of full with cancer. It looks bad actually, and that is actually one of the characteristics of ER plus patient, that the cancer is more aggressive, it spreads more rapidly, and visually it can sort of like be seen. However, it's pretty much it's observation, right? Of course, pathologists, having practiced this field for 20, 30, 40 years, can tell you with some sort of accuracy that, oh, the tissue I'm looking is ER positive. However, the challenge is like, how can I actually bring this to a medical device level, right? How can we bring this so that people can use it to make clinical diagnostic decision making? And yeah, the idea is quite simple, right? There are some patterns that only exist in the negative cases, right? There are some patterns that are observed in both, and there are some patterns that only exist in the positive cases. And our task as well, the platform's task is pretty much to figure out which morphology is predictive of this tissue being positive or negative, i.e., which morphology are sort of differentiating between these 2 classes, right? Now, sort of like, arriving at this machine learning elements where we try to figure out certain patterns, right? Again, on a very high level, one can apply, let's say, certain encoding network. Of course, our network internally is way more complicated than this, but on an extremely high level, one can understand that there should be an encoder that encodes certain input into certain embedding, right? So that the embeddings coming from two patients of the same class, they would have, very similar features, while the embeddings that are coming from two different class would be different. Very simple. Of course, being medical devices, there are a lot of requirements, right? The image itself is actually massive. One tissue scan is around about half a gig to 20 gigabyte. So that's like almost like a significant amount of image net. And for us to be able to figure out patterns that are predictive of this being positive or negative requires us to sort of take a look into tens of thousands of patients. And of course, those signals need to be consistent, right? So, a lot of engineering, a lot of research activities were spent on trying to make sure that the signal is of very high quality, that the signal is repeatable, is reliable, et cetera, et cetera, et cetera. So that's what we do on extremely high level. And we actually recently received a clinical approval for our first device. So the idea is, as I mentioned before, right, we have this tissue scans coming from the patient. And what we can do is, we can apply our methods on those tissues and provides this biomarker status. So the idea is, if we can do that, we can therefore replace the existing ER, PR, and HER2 tests in clinical setting. All these expensive, time-consuming, and not accessible tests, we can get away with that, meaning that we can, diagnose diseases or diagnose cancer, or in this case, breast cancer, way, way more quickly. The device pretty much takes less than 10 minutes to diagnose a disease or to profile the tissue. Normal ER, PR, HER2 usually takes up to 2 weeks. So, you can actually see the time acceleration. It is way cheaper. I mean, it is technically computational, so it doesn't cost us anything. But, as a business, of course, we take some values out of it. But even comparing that to the existing tests, we're looking at like extreme sort of savings coming from the fact that we don't have to maintain a lab, we don't have to employ this biomedical scientist, we don't have to buy extremely expensive reagents, et cetera, et cetera, et cetera. And one thing that is exciting is actually our device, as it stood in our clinical validation, has actually better accuracy than existing tests. What it means is, we can not only provide a, faster, cheaper, more accessible alternative to the molecular test, we can actually provide a better result. So I don't know, some of you might have been looking into the COVID test, for example, right? If you got symptom, the first thing you do is actually do lateral flow. And only if you test positive, the NHS will send you over the PCR. The reason why they do this is because PCR actually has better accuracy. So that is actually the one that is used to diagnose COVID. The lateral flow is some sort of qualifier. So what we can do is we can provide better alternative than existing tests, meaning that we can actually reduce the frequency of someone being misdiagnosed with cancer. So misdiagnosed can be very bad, especially if one is treated with the treatment that is not necessarily, sort of fitting into that person. In the worst case, or in the best case, the person doesn't get cured, right? In the worst case is some of the treatment actually extremely toxic. So, you can imagine there would be sort of like events or sort of like negative adverse effect associated with the treatment. So what we can do is we can potentially reduce that once having the device applied in clinical setting. Yeah, and of course, having done the clinical validation, we have actually received approval for device in the EU and UK, which is actually the first time such device is ever allowed for clinical use. Yeah, and the way we see it is, cancer is becoming increasingly precise sort of disease. A lot of resources spent on research means that we as humanity understand cancer better, meaning that we can target cancer better, meaning that, before we can even do anything about it, we have to get the full information, right? So I don't know if some of you sort of know how a cancer treatment or drug is being developed. It usually, sort of goes this pathway of the discovery of a certain targets within the body that are relevant, followed by discovery or the development of the drugs. And this drug will then, undergo the sequence of validation. The first one being the sort of validation in the lab, where they try to understand the kinetics, the dynamics, and how the drugs react or interact with certain molecules within the body. It then undergo this trial on animals and then human, and there would be three phases of that. And if the results are good, then the drug will be approved. And our source solution can be used pretty much across this drug development. So, early on, we can actually help pharma develop better drug, make them understand better, right, which molecular signature in the body does the drug actually target, defining better target, for the drug. We can actually also improve the probability of the drug succeeding clinical trials. So as you can imagine, I don't know if some of you here may be doing some wet lab, a lot of experiments or trials for cancer drugs or for any drugs in that matter, it can fail. I don't know if you follow the news, for example, when the pandemic started, right? There were actually a lot of companies developing vaccines. At the end, only 4 or 5 succeeded in developing it or in getting the approval. So what we can do is we can actually improve the probability of cancer drug sort of, working on the patient, being approved, and i.e. actually impacting, humans' life positively. Right now, the probability of the drug failing the trial is actually around 90%. So we can actually improve that, and meaning that we would have better treatment for especially deadly diseases or deadly type of cancer like lung, for example. And yeah, down the line, of course, with the idea of understanding the molecular characteristics of cancer, or the motivation of which is to sort of, provide a better and more precise treatment for the patient, using our platform can, at the end of the day, allow people to actually target patient better for us or for the clinicians to actually commission certain or more appropriate treatment for the patient. So that's like how we see ourselves. And yeah, I don't know if some of you might be graduating soon or looking for internship. As always, as a company, we were growing. Our team doubled in the last 12 months. We're looking to triple our team size in the next year. We're hiring for ML engineers, so we are building a platform, right? We are training a lot of models daily. I think it's around like 1 to 2,000 models per day. So ML engineer, pretty much a very important aspect of our company. We want to enable ourselves and our pharmaceutical partners to train 10,000 models on our platform today. A lot of engineering challenges, a lot of scalability challenges, right? Can we enable that? We also are hiring for ML data scientists. So as a company, we work with pharmaceutical companies, right? Develop better treatments, better drugs, or allow them to design their trials so that they would be more successful. So we're also looking for people who would love to actually work with pharma, delivering better drugs using our platform. We're also hiring for tech lead. I don't know if some of you happen to have a lot of experience in engineering before. We're also looking to hire a tech lead to lead our teams building better platform for ourselves and for the pharmaceutical companies. So yeah, that's pretty much it. And yeah, I have my email over here. Just shoot out some email if you guys are interested, or just forward to your friends or something. And yeah, I guess that's it. Yeah. Cool. Any question or comments or? Yes.
So, what was the largest barrier you would say to developing this technology?
The largest barrier is, I guess, initially getting clinical data, because, right, the imaging data, the tissue, like the histological imaging data, they are mostly coming from comprehensive cancer centers. It is patient data, so we have to deal with a lot of regulatory and ethical considerations when collecting and storing those data. I think beyond that, the challenge is, of course, trying to sort of understand or trying to develop something that is extremely reliable. You know, people like to think in terms of AUC, accuracy, all this sort of metric. Of course, we are very concerned with those metrics, but what is more important for us is, sure, the method looks great on the paper. Internally, can we commit on having the method deployed in the hospital, right? Because if it is not predicting properly, you know, in the same way that if the current tests do not perform properly, then a patient might be receiving a treatment that is not supposed to be assigned to the patient, right? You know, you can see cases of, you know, misdiagnosis or toxicity event, which could be lethal. So a lot of consideration around, are we really looking at the number that we can trust, right? So we spend a lot of resources actually around explainability, interpretability, you know, generalizability. Pretty much a lot of the work, I would say the majority of the work of our research team are actually building reliable AI, you know, pushing beyond what people currently have in the state of the art. Yeah, that's, I think, challenge. Yes.
You said that you're kind of using the platform to help develop better drugs and the biomarkers.
Yeah.
How can you do that just by imaging? Because with the ER example, I understand that you're looking at morphological
Yes.
factors.
Yeah. So one of the challenge, actually a lot of challenge in drug discovery. One of the challenge, especially in the early stages, the lack of availability of samples, because, you know, tissue is being taken from the patient, from animals, right? From nowadays, they also use this fancy, you know, organoid, for example, right? The organs are sort of fake, not fake, but like, you know, model organs that are developed in the lab. And a lot of the times, actually, they need to see, right, how that tissue that we are looking at responds to certain chemical treatment. And, you know, what happens most of the time is, given that all these experiments are extremely expensive, you cannot A, do a lot of tests, a lot of experiments on the tissue, right? And B, even if you can do a lot of experiments, there is actually a lack of samples, right? And a lot of these tests, they need to consume the tissue, right? You know, because the tissue need to be either crushed or stained or somehow processed biochemically or physically, and then undergo certain tests. And you cannot just say, I'm going to run 5,000 tests on that tissue, because you only have this very small tissue, and after 20 tests, you would be out of tissue. So what we can do is, by allowing the pharmaceutical companies to run the digital tests, it doesn't require them to consume the tissue, which is actually extremely valuable, because, you know, even, I guess organ lab tissue, at least it only costs money, right? A patient tissue requires a patient with known disease, and there are not many of them, right? And either they would die, unfortunately, or they would be cured, so the tissue doesn't exist anymore. So it's just like the limitation of tissue, and for us being able to provide a lot of information without doing the test, without consuming the tissue, doing pretty much thousands of tests. So right now we can actually do 3,000 sort of profiles without ever consuming the tissue is extremely powerful and useful for them. Yes.
Yeah, as you mentioned, false negative cases will be detrimental to.
Yes.
Then how do you tackle those issues? Like how do you increase the call?
Yeah. It generally depends on the treatment. ER is not as toxic as other treatment. It is actually, it is still toxic in the sense like, one can get, is actually cardiotoxic, but it is actually acceptable to apply ER or apply tamoxifen on breast cancer patient. Some other treatments are actually extremely toxic. So, as you said, right, false positive is bad. False negative is not necessarily bad, but it is ethically very bad because you are denying treatment. There's a special category of hell for people in medical community who actually deny treatment to patient. In terms of how we solving that, there are a lot of approach, technically or on approach level. Of course, we try to sort of pick as good signal as possible, right? One thing that we can do is, of course, there are a lot of ML approaches, right? Hard negative, hard positive, contrastive, all the sort of approaches that are out there. We sort of push it a little bit because a lot of those problems deal with pictures of cats and dogs and people or picture on streets from Google Map, which are not really relevant for us. For us, actually, the signals are very subtle, right? We look at this tissue, for example. I just took a very good example of 4 tissues, but in reality, there are a lot of signals that are actually hard to discern. So it is our task to, get way or very high quality signals. How do we get that? Of course, build better models, get more tissues, right? The signals that you can get from 100 tissue will be different from the signal you can get from 10,000 tissues, right? So second approach. Another thing is we have this method that actually force the models to only make the call if they are very certain. One thing that one can do is actually, thinking in terms of uncertainty, right? Of course, uncertainty and in clinical use cases or in use cases that are highly or that require highly reliable accuracy, for example, in industrial application, right? If you are actually using ML to do motion control in certain factory machines, right? You need to be sure that whatever it does is extremely reliable. So we actually taking a lot of approaches from the same sort of people who are developing, ML in reliable application, like motion control in airplane, etc. So forcing the model to be extremely conservative, not making a call when it doesn't think it really is certain about the call, things like that. Yes.
Yeah, so you talked about creating a molecular profile.
Yes.
From the imaging data. So what kind of molecular profile you are able to infer?
Yes.
Or is the model just is a classifier? And the second part to that question is, let's say you created a molecular profile. Does your model have some kind of explanation, like why, like what it's seen in the data that make the model infer a particular one?
Yeah. So in terms of what we're doing, we're pretty much doing it multiomics. So, sort of fundamental dogma in biochemistry, right? From the DNA, we can predict mutation, all these alterations, insertion, deletion, copy number of genes, etc. We can predict the mRNA, right? The, transcriptomics expression levels, certain modification of the mRNA, right? It is increasingly important. We can predict protein expression levels. Is it underexpressed, overexpressed? Again, very important for a lot of diagnostic use cases. We can predict metabolomics, for example, we can actually see if there are certain over representation of certain pathways, right? I mean, some of the pathways within the cell are relevant for cancer, for example, cell division, right? So a lot of amino acid related pathways, we can predict that. We can even predict outcome, based on the results or based on the tissue. We can tell if the person would survive or respond to certain treatment. That's like a bit more avant-garde use cases. It is actually the one that oncology is very interested, because what is the whole purpose of this extremely expensive, time-consuming test? It's actually trying to see if the patient would respond to a certain treatment, right? So we can do that. Yeah, so that's like answering your question. I think the second question was around
The explainability, like why
Yes.
the model is different.
Yes, explainability. We do a lot of explainable. One of the most common example is when it comes to predicting certain cancer-bound biomarkers. For example, ER. When we are doing estrogen receptor prediction, it is actually, we're doing prediction on the expression level of ER on cancer cells, right? So one of the things that we do internally is this sort of like a sampling approach or sampling module that we have. The task of this module is to pick which part of the tissues are relevant for the downstream prediction. Of course, it is an ML approach, so it is black box. So what we can do is actually, we can see, right, the saliency map or matrix of the tissue, right? Which parts of tissue the pipeline is picking up, right? Is it picking up on picking up mostly cancerous tissues, or does it also pick up fat tissue, for example? Fat tissue is well understood to not contain any information because sort of makes sense, right? It only contains fat. So if the model, for example, focus on fat, despite it being correct, it might be some confounding factor, right? There might be some happenstance. So we're actually doing a lot of these things. A lot of things that we are doing actually have this sort of user interaction. So we build a lot of integration, for example, of the model with our clinicians, right? If a model is being trained, what we like to do, first thing is on top of the standard metrics, looking at the saliency, for example, is it focused on wrong area? Or another thing that is interesting is some sort of confounding factor analysis, right? When the model predicts something being positive, for example, is it predicting it being positive because it so happens that one hospital actually provides most of the positive cases, and you can actually see the staining looks different, right? So trying to normalize the prediction so that it doesn't actually predict anything that is not necessarily relevant is also important for us. So we have all these sort of things. Our duty or our responsibilities as developer of medical device is actually to understand or to enable ourselves and our clinical partners to understand what the device is doing, because ML model is notoriously hard to understand. Our approach, being computational molecular test, is even more harder to understand than some simple scene classifier, right? So you can actually see a lot of challenges are being confounded by the fact that we have to develop something that is used, that can be used in clinical purposes. Yes. Oh, cool. Maybe that one first.
I have a question. You were saying that your model performs better than like the state of the art.
Yes.
Do you compare it to when a doctor looks at a molecule using a microscope or using the web tests?
So the way a lot of tests are being done is it applies certain reagent, certain chemical compound on the tissue or process tissue, right? Be it you sequence it and you get the readout, right? The genetic sequencing, or you get this sort of expression of certain markers on the tissue. So imagine if you're doing ER here, you would actually see the cells that are expressing ER on that tissue. or it could, have certain physical reading, for example, some time series, right? A lot of spectroscopy actually provide time series, which needs to be interpreted. So there are a lot of events that happen. For example, for ER, what happens is the tissue are stained with certain coloring, and it would sort of change the tissue color based on the status of the cell. And the pathologist would sort of analyze that, and the final call is being made based on the change in color. And what happens is, this can be wrong. There's actually, depending on which studies you cite, there are anywhere between 5 to 20% sort of like misclassification. How do they figure it out is, sort of simply following up the patient. If the patient, let's say, was being subtyped as ER positive, they would receive the tamoxifen, right? And then, sometimes the patient doesn't respond. And it is extremely common if sometimes the patient doesn't respond, the case is being revisited. And that's like when they figure out, oh, actually the test was wrong, or the diagnosis or the analysis was wrong. So what we're comparing it against the sort of follow-up cases where it is known that, certain wrong predictions are being made and sort of annotated, and we compare ourselves against that, and pretty much we are looking at improvement compared to the baseline, which is the ER staining test. Yes, sorry.
So like so for medical image data sets,
Yes.
labeling would be very costly.
Yes.
So then do you use like all label data set like a supervised training, or do you use like self-supervised to decrease the cost?
So we have a lot of intermediate steps on the way to making the final decision, right? For example, one of the most common things that we are doing is detecting cancer from the tissue. Initially, of course, we have pathologists. We have 2 pathologists and 1 biomedical scientist in-house that annotate the image, and it took them like easy 8 to 16 hours just to annotate 1 image. Of course, we do a lot of like optimization. We do sort of weak model approach, right? There's actually you can train easily some models that pretty much predict 80% of the cases, and they just modify the annotation on 20% of the time, right? So that pretty much taking the 80% out of 100%, letting them only focus on 20%. Another thing that we do is sort of guiding them, showing the parts that are relevant, because let's say you have tissues that only contain cancer. There's actually no point of annotating that because it's not really informative. What is informative is, for example, the area, the boundary between cancer and normal tissue, right? Because those are the morphologically or feature-wise very relevant, knowing where to stop segmenting something being cancer or not. Of course, once you have all this insight, we also do a lot of semi-supervised, unsupervised approach. Cancer cells look quite distinct because it is not normal. Having seen a lot of tissue imaging myself, I can tell if something is cancerous, even on other organ, which I haven't seen. And pretty much the same approach can be done to sort of like detect cancer. Of course, doing something like using our sampling is increasingly being implemented as a non-supervised because, sometimes it doesn't really matter, or it matters less that the prediction module predict on cancer or non-cancer tissues. It matters that actually predicts based on informative region, right? And sometimes the informative regions are not necessarily cancer, for example. Within the medical community, it is well understood that the area where white blood cells are infiltrating cancers, they're actually extremely informative, and those are not cancerous, for example. So we go by the principle that yes, there are some area or there are some regions where it doesn't make sense for the model to be focused on, for example, fat tissue. But sometimes you have all this gray area, and if anything, the gray area is actually the widest, because a lot of these things aren't even studied, right? And for us, developing something that is not been done before means that we have to deal with all the signals that aren't necessarily been discovered before, which is actually very interesting because we have seen examples of our model performing extremely well, confounding free, sort of makes sense, right? There is no bias, and so far that we can tell using our explainability modules, but it focuses on parts of the tissue that aren't necessarily considered to be informative. And in that scenario is, if the signal indicates, or if the signal seems to make sense, it might actually make sense, right? And one of the things that we are increasingly doing a lot of research with our clinical partners is trying to understand what are those, right? If the models keep picking up this part of the tissue, what is it? Maybe it is something that can in turn be used to treat the patient better, right? To develop better drugs, et cetera, et cetera, et cetera. Yes.
I was wondering how you navigated the clinical trials and was
I
it
see.
difficult?
It's different.
I imagine it's very different molecular.
Oh yeah. I mean, we even our clinical teams, they don't have experience in clinical trial. I did some clinical trials in the past because as part of my biomathematics sort of gigs, I design trials, trying to prove that certain design delivers certain significance, right? This sort of like statistical experiment design. However, it is difficult because again, going back to the data, right? It is a patient data. It is a disease that is deadly. Most of the time, one can actually tell based on patient information if the person died or not, because the patient, look at the tissue. It is a let's say stage 4 breast cancer. The patient is 75 with a history of smoking and alcoholism. 95% the person would be dead already. So you're dealing actually with very sensitive information, right? A lot of information that have a lot of ethical loading. Having said that, a lot of those are actually regulated, right? From simple regulation like GDPR, there's Human Tissue Act, there are tens of thousands of regulations we need to adhere to. A lot of those are actually already embedded within our company. So pretty much our ML scientists and engineers, they don't have to go through this regulatory training. But even building this regulatory features within our pipeline is difficult because you have to read the regulations, right? They're like, I don't know, four laws that we have to follow in UK when it comes to medical devices, and we sort of have to implement that within our platform. So a lot of those are actually already done, but even despite that, actually, when a new regulation comes, what happens is we actually have regulatory team in-house. So our engineer would work with them and the clinicians, for example, in trying to implement that part of regulatory that hasn't been implemented, for example. So that's why as a company, we're actually very multidisciplinary. We have clinicians in our ML research meetings. We always have pathologists sort of attending the meeting, even though we don't understand. At least, whenever something that is potentially relevant, we can always sort of talk to them, things like that.
But if you want to expand beyond the UK and the EU, does that potentially mean that you might have to change?
So it's more like usually adding stuff. It's not necessarily changing because the principle of the regulatory considerations in medical devices actually pretty much similar, as in a medical device has to be safe and effective. And the definition of it being safe and effective is actually quite unified across the board. There are some variations, but again, these variations will need to be implemented. So it goes back to, having, for example, models that handle English or German or Chinese in things like Alexa, for example. So we have the sort of modules for various regulatory considerations. I think someone. Yes.
What
So you have both engineering and research ML teams.
Yes.
What would you describe as like, say, a difference between the two?
So research is pretty much, I call it pushing boundaries, because a lot of our questions, there are growing literature around computational pathology, but a lot of them, sort of focus on preclinical, oh, can we do that at, I don't know, bidding the AUC, classic, right? You bid it by 0.3, you publish it in Kai. Don't really care about that. What we care is actually whatever that we do needs to be reliable. So there is actually a niche element of developing a safe and reliable ML. It is increasingly studied nowadays within the research community. However, even within that, a lot of the problems that we deal internally, it's not something that's necessarily solved or being addressed within the research community. So we have to actually push our own boundary. So a lot of the research team's work is actually pushing these boundaries. We are planning to publish some results as early as next year. Right now, we are still kind of small to do that because we focus actually on pushing the medical device. But there are a lot of discoveries that we've done that actually, if you think about it, nobody else has done, because of course, this is a very specific company working on specific problem with specific requirements that can be actually relevant for other companies. The engineering, I think putting it that way, I mean, the way we see it is, the ML engineer sort of like enables our research team to do better research. So a lot of the things that happen within the company is, there are actually some challenges that are relevant or specific for us. For example, the size of imaging, right? Our image is, anywhere between, as I said, right, half a gig to 20, 30 gig. One biomarker within one disease easily would have, let's say, 10,000 patients. And now you want to train, or you want to pick the model or a signal that is so subtle that, you have to do, I don't know, 100 repetition just to figure out that the signal is actually relevant and reliable. So, we build a lot of platform elements on that, right? So when a method is being developed, how would that work that this method being developed, merge into our branch or a certain branch within our code base goes from here, get the data that's appropriate, get the data that is actually representative to population, train in a way that, let's say that it can be trained on this big population, many hundred times, and train in a way that, the validation of which is reliable, right? Making sure that the tests, the training, the validation, the tests sort of like represent certain characteristics, right? Normalizing the validation so that it's not biased, looking into the explainability. So a lot of things that engineering platform sort of team is doing is actually the explainability component, right? Connecting it to our other system, which connects to pathologists, for example, right? Providing the information to the clinical experts who can actually see that the device is working well, et cetera. So, it's pretty much like building a, Tesla rocket, but in a sort of ML setting, right? You run engineering experiments, you have a combustion or you have propulsion, you get all this data, it has to be sent, it has to be stored somewhere, it has to be presented in a way that people can understand, et cetera, et cetera, et cetera, at the same time allowing literally tens of thousands of models to be trained for one use case. So one of the things that we are doing is actually I mentioned about we can do 3,000 biomarkers right now. So this is actually one of the project of our platform team actually. Oh, can we predict any sort of mutation in any relevant genes in any cancer types that are known to humanity, right? So, a lot of engineering works are involved in this, for example, right? Cool. Yes.
Just another question. So you're using data like images,
Yes.
your images
Yes.
from biopsy,
Yes.
but that will require some time because you have to do the incision and extract the tissue.
Yes.
So my question is, why don't we just simply use like radiology images?
Yeah.
Would
So
that lead to like lower performance?
So I think one of the beautiful thing about our platform is because a lot of them have been modified or have been improved in a way that it is almost unsupervised. Pretty much if you give us a radiology information, or let's say, radiography imaging and certain output or certain outcome, we can tell if it is predictable, right? To what extent it is predictable, what is predictability rate, whatever metrics you use. And we can actually tell somehow or somewhat that can we commit that as a medical device or use case that can be used by pharma or clinical researcher. Fundamentally though, radiography is different than pathology because I think we have this one example, right? Just from the dimension perspective, it is, way different because radiography, you deal with macro level, right? It is your body. You can tell actually there's some calcification, there's some dynamics on sub macro level, for example, that 1 millimeter sort of scale. However, going deep to the cellular level, because actually there are a lot of, for example, cancer is highly associated with calcification because cancer cells keeps on dividing and dying, and those in turn produce a lot of calcium, right, in the area. A lot of other tissues actually are showing this sort of dynamics, and in the inverse, a lot of cancers do not actually show calcification, or there are actually various subtypes of cancer, right? There are, there are like, for example, 2-3 major types of breast cancer, and those are not discernible on radiography, for example. So the way I see it is there is the macro level, right? The anatomical radiography, and then there's a micro level, the pathology, and there's a molecular one. So, and for us is pathology is actually not that challenging on its own because the tissue nowadays, the way tissue is being taken is actually quite straightforward. They have a specialized device that sort of puncture without having, without requiring surgery, and just takes the tissue. Full analysis can be done. Molecular, on the other hand, for us at least right now, is the bottleneck. If we think that, in the previous mention, right, India has the same number of pathologists despite being 20 times bigger. It is already specialized. However, molecular pathology, the molecular element is even more specialized. Some biomarkers needs to be tested in the US just because there is no hospital outside the US that can do those tests, for example. So definitely a bigger problem, at least where we are right now. But I totally can see a lot of things can be done in radiology. I don't know if you read last year when pandemic just started, there's actually some research going on trying to see if someone is or got COVID just by looking at the lung CT, right? One can actually do that. It is actually established that a lot of diseases can be diagnosed without going to tissue level. There are actually some methods like MRI, which can go very, very, on a very granular level. However, I think it goes back to if you go on that level, the amount of data that this method produces will be way higher than the pathology imaging that it just makes sense to take the tissue sample.
For any more questions, feel free to stick around, but let's thank our speaker.
Cool. Thanks.